Okay, good morning. I hope everyone can hear me. This is a little bit hard to tell, so if you can't
Yes.
okay, that's good. If somebody gives me audio feedback. Good. Hello, welcome everyone to Statistics for Data Science, which is a module in the Master Data Science. I'm Dirk Ostwald, Professor for Computational Cognitive Neuroscience, and I'm teaching this module this academic year, and this module is only happening in the winter term 2020-21. Today we have the first session, and of course it's an introductory session, so I assume you had many introductory sessions already this week. So I will go a little bit about what or where I see this course, Statistics for Data Science, situated in the bigger picture of data science. And then, of course, another important thing today is to discuss the formalities of the course so that you know what you have to do to get your credits for the course Statistics in Data Science. As you know, the course Statistics for Data Science comprises two main units, namely this lecture, which is happening at 7:30 on Friday. It is being recorded, so everybody by now should be informed that this is being recorded, and it will be posted online on my YouTube channel. If we enter kind of discussions and so on, I will make sure that most of that is actually not present in the video, so we will kind of structure things like that. When I'm talking, that will be what will be then online, and if we then enter discussions, this will usually then not be online. Which also means that you may or may not want to attend this lecture in a synchronized framework, meaning that you actually join at 7:30 on Fridays, which you are happy to do, so feel free. I think it's a good thing, and we can actually then address questions. So it's good, and yeah. On the other hand, you can see it that I'm just recording these lectures 7:30 on Friday, and you then watch them later, whatever works best for you. The other big unit that we are doing is the Übung exercise unit, which takes place in a more or less synchronous manner on Fridays at 1 p.m. And this will or will not happen today. That depends a little bit on how fast we get through everything. So these are the big two units of this course, and what they entail and what we are going to do there and what the formalities are and so on. This is what then I will try to develop over the course of this lecture today. I think I will then first go. So there are big blocks for questions put into today's session. So everything that you are keen on learning and clarifying about the course, we can definitely then do at these times. But let me first start and give you a little bit an idea of where I see this course and how it relates to data science. So, data science. My personal definition of data science is that data science is the art of creating meaning from data. And by data, I mainly have in mind quantitative data that is present in digital form. And you can even make the scope bigger for data science, that it may also include qualitative data, and also in a way qualitative data analysis is also of course data science. But what I'm mainly concerned with in my own work as a computational cognitive neuroscientist is of course quantitative digital data. And there are it depends always a little bit on whom you ask. So computer scientists, from my perspective, are very good in organizing data and getting data in a way that data scientists can then create meaning from that. Mathematicians can think about ways to analyze data, but they then usually often shy a little bit away from actually then doing that. And of course, data scientists try to do the whole thing. So why a master in data science? So this actually goes back to an initiative that I started in 2016. Things blur a little bit if I look into my past working life, because something is always going on. So I think in 2015, 2016 or so, the Freie Universität was thinking about how they can get ready for the digital age. And a colleague of mine, Hauke Hekerin, who's now vice president, he was part, I think, of one of these steering committees where they talked about how to set up the Freie Universität for the digital age. And he said, there were some ideas of how to make the administration more digital and so on, but there was nothing about teaching. So what does it mean to enter the digital age also in terms of teaching content, and of course not in terms of teaching by WebEx and so on, but in teaching content. And I said, well, that's fairly obvious. There needs to be a program in data science, because by 2015-16 there were of course already data science programs at other universities outside of Germany, so not in Germany. I think there was hardly one, if at all. But other universities had already taken up that. And it also was quite obvious for me, because since I joined the neuroimaging field, or the computational cognitive neuroscience field, however you want to call it, which was in 2005, I realized that the really interesting, or the challenging and interesting and nice, cool stuff is actually in data science. So in basically having data available that you recorded, for example, using an experiment, but then it's not that the data just speak for themselves and you just record the data, for example, as we do with brain imaging scanners, and then the data is recorded and is nicely organized, maybe even in a in some kind of I always forget the term, data warehouse kind of setting, and then there is something to tell and something to communicate, but then actually the real work starts in terms of the applied mathematics of understanding what kind of methods are being applied and what they then actually mean, and also in starting to being creative and developing your own data analytical methods to create meaning from the data, because without this interaction or this intervention of a human there, nothing will happen. So I said, okay, we should start this master data science, and then we, of course, because we with the neuroimaging people, the cognitive neuroscientists, we are situated in psychology. Of course, I said it would be a good thing to do that together with mathematics and computer science, because that feels fairly natural. So we wrote something and we asked computer science and mathematics, and then it took, I think, like 1 or 2 years, I think more like 2 years, where nothing was happening because our computer science and mathematics department, they are not really that much into data science. I mean, there is one part of computer science, so the Rojas group, which has always done things like in artificial intelligence, so they were set up with that, but Professor Rojas was kind of nearing retirement, and the rest of computer science really was not that much into data science. And in mathematics, it's was a little bit less clear what's actually going on there, but they have a strong focus on bioinformatics. But then at one point, Tim Conrad got interested in also following up data science, and then we developed this study program. And then at one point also computer science finally joined in with Katinka, and I think you met all of them. And then we started, after developing this the study regulations and so on, then the master data science finally started last year. So that's a little bit the history of your study program and my personal understanding of data science. It's an art, so for me science and arts are the same thing. It's just different rules that apply, and it's about creating meaning, because data without data science is just if you want bits stored on a computer, but that doesn't mean anything to humans per se. Now a little bit more in depth, where how I see where I see data science situated. I might have shown that previously. So of course, data science builds on things that have been around forever, and also the term data science is not really new, so that's a term from kind of the 1950s. Of course, it builds strongly, and this is really where I see data science coming from, statistics. So from the 19th to the 20th century, statistics always has been around, and probability theory has been around, and the idea was always to apply the ideas of probability theory to real world problems. So in a way, that's statistics. So Maurizio cannot hear anything, but I guess the rest of the people can hear something. That's good. Statistics has been around for a long time, and then of course in the mid 20th century, computers came around, and of course computers can help applied mathematics a lot, and hence they also factor into this data science idea, so analyzing data. And as you all know, since kind of the maybe the 1990s, statistics is learned and studied by computer scientists, and then maybe here and there develop a little bit further, is called machine learning, which is a little bit of a weird term, but nevertheless it exists, and you all are aware that certain statistical topics are dealt with in machine learning. But these two things, so computer science and programming, so implementing the ideas of applied mathematics and statistics, are not everything that play a role in data science and also carrying out data science projects. Of course, the data science always has kind of an applied perspective with some concrete problem in mind, and to create meaning from data with a concrete problem in mind, of course it needs some general ideas about the problem at hand, so it needs a disciplinary expertise. And of course from the different disciplines there is some overlap into computer science and mathematics. So when I'm speaking from my perspective as a computational cognitive neuroscientist, of course the data that we record with our brain imaging devices like MR scanners or EEG. Of course, that always, since I'm around, so in 2005, has been there in digital form. You might know that EEG in the old days was written on paper, but so using a machine, but that wrote on paper. But this has been digitalized, so there is a natural relation if you record digital data to computer science and programming, because you have digital data and it's there, so you need to do something with it, and then programming is or programming a computer to do that is a nice way to save you some work. And on the other hand, from my perspective, again, from cognitive neuroscience, of course, we are interested in quantitative research, and yeah, as you look at the developments of the sciences, of course, physics has always been kind of, or has been one of the first domains that went quantitative. But then you also know that, for example, biology and also psychology and medicine got more and more into kind of this physics approach to things, of having phenomena, trying to describe them quantitatively and making predictions. So there is, I think, in all disciplines by now, a large overlap with digital data on the one hand, because I think data is hardly stored in non-digital form, so it needs people who can deal with digital data. And in general, although there are good reasons to doing in the sciences, so not the humanities, but in the sciences, there are good reasons to also do qualitative work. There is also a strong interest in quantitative research, which is then the realm of mathematics and statistics. So, and in between all of this, that's where data science sits, or that's what I call data science. Let's say like this. Before we go a little bit further, two general remarks of my approach to data science or data analysis. So one thing that I always think of when thinking about data analysis or data science is that it's a form of data reduction. So usually the digital data sets that we're dealing with are fairly high dimensional, so there are many data points, but humans can deal with things better if some of the complexities or some of the let's call them noise or nuisances are removed, and if things are kind of reduced. So any form of data analysis from my perspective is data reduction. Think of medical examples where you have many features that maybe refer to symptoms of participants who may or may not have COVID. In the end, you want to know, do they have COVID or not? So you get a kind of a binary variable, and you reduce this big information to a large information set to a reduced information set. And I think, essentially that's happening all the time. So it's always there's always a data reduction step, and of course the art is to first of all make this data reduction step meaningful, to understand what's going on there, and and then also find good summaries of data. The other thing that, from my perspective, is the case for all data analytical method is that it's model-based. So this data reduction step is never done in a kind of objective, data-driven, model-free, let the data speak for themselves way. I know that some people think of certain methods like that, for example, independent component analysis or all these kind of dimensionality reduction systems, but that's completely not sensible, because of course these data reduction or feature extraction things like ICA and so on, they build in strong assumption of what they emphasize in data and whatnot. So all data analysis is model based, and this is essentially also just the scientific paradigm here. So there is something that you might call reality, and from reality you sample certain aspects and record them and have them in digital form. That's what you call data. And then you want to make some sense about reality by formulating a quantitative model. And then you want to relate your quantitative model to the data, which I call model estimation. And then you want to evaluate this model, for example, whether it's making good predictions or whether certain parameters or estimates are unlikely to arise from chance in kind of hypothesis testing. And then you want to build a better model. And of course, this is the same idea as this Cox, I think it's Cox quote, like all models are wrong, but some models are useful. Of course, the idea is to have useful models, and what useful models are, of course, depends strongly on the context. In science, useful models can also be models that are interesting to humans. If you build a plane, a good model is a model, whether it's actually mimicking reality well or not, but it's a model that keeps planes in the air and not makes them crash. So, but everything is model-based. You will not find any kind of data analytical technique in machine learning, artificial intelligence, or statistics that is not model-based. If you find one, let's discuss it, and I will show you the model in it. Because this is then the last aspect in terms of these general remarks on data analysis. It's an interpretive device. Yeah, like I said, the data themselves, if they are stored in digital format, it's zeros and ones, and some of these aspects are then interesting and useful for certain applications, and others less so. Maybe all of them are. Can also be, but that's then just a special case of that certain aspects are useful. Whatever kind of data analytical procedure you use, it's kind of like a lens or a looking glass where you try to or where you emphasize certain aspects of the data and neglect others. For example, because you say they are noise, meaning that they don't help you in making sense of the data. Yeah, so that's kind of the way I see all kind of data analytical methods and all things that people do in data analysis. So it's always data reduction, it's always based on a model, and of course it's always a means to interpret data to create meaning from data. From my perspective, I don't differentiate between data science, statistics, machine learning, and AI. So I'm fairly close to what Michael Jordan, who you may or may not know, talks about. So if you're interested in who Michael Jordan is, and so it's not the basketball player, and what his ideas about data science are, you might either have a look at my machine learning course from last summer term, which you find on my teaching website. I feature Michael Jordan there a bit, so not him live, but some of his quotes and so on. And there's also there's this podcast by this Harvard guy, I forgot his name right now, who's interviewing all the big shots right now, and he also has Michael Jordan. So if you Google YouTube Michael Jordan statistics, he's a very reasonable person, and he's well read, he knows a lot, and he is very reasonable, so it makes sense to listen to him. And so there, from my perspective, all of these things, so he has this idea of data engineering mainly in mind, which kind of overlaps with a data science, although I'm always a little bit, with engineering, at least in Germany, I'm a little bit data engineering has, from my, or at least if you're at a German university and you hear engineering, that's kind of, okay, mathematics tries to be very precise, physics makes some approximations, and engineering makes even stronger approximations. So in engineering, of course, the aim is to get something to work and maybe less to understand what's going on. So I'm not completely agree with Michael Jordan in this idea of data engineering, but the philosophy is the same. So that statistics, machine learning, AI, and data science are essentially all the same thing. Although, and this is what this slide is of course supposed to show, is that they emphasize different aspects. And statistics, as we will see, of course has a strong focus on probability theory. It's quite strongly theory and optimality oriented. So the question is, are these things good that we are doing? And can we say that things are good in general, and maybe things are good in terms of asymptotics if we have a lot of data. So that's kind of the main focus of statistics. Of course, if you go more into frequentist Bayesian statistics, at one point you end up in science philosophy, which is also interesting. But this is what people usually think of when talking about statistics. Machine learning, I put here deterministic models first, because you might know that neural networks and deep learning approaches are not probabilistic models, so they don't rest on a probabilistic framework. Similar if you look at SVMs in their most basic form. So machine learning, you can read a machine learning book and you don't need to read a lot of probability theory first. However, machine learning, of course, also has at many occasions strong links to probability theory for some time before the 2010s. So when I first entered the machine learning field, so for example, when I was at the machine learning summer school in 2007, I think it was, that was before neural networks were of interest to people again. That's when machine learning was really interested in Bayesian models, and there's and you might know the term probabilistic programming. That's which is now one thing that kind of the Bayesian people are in machine learning are developing. So people like Chris Bishop. You might also know the term variational autoencoders from deep learning. These are of course all probabilistic models. So machine learning also can have probabilistic models, but the machine learning that you might encounter if you type in machine learning and then you learn that machine learning, the only thing that in machine learning exists are neural networks, then of course you are out of the probabilistic domain first. And then machine learning, of course, has their benchmarking set, so it's a community and they have their benchmark sets, the IMNES set, and they try to get better in that. And of course, machine learning is also fairly application centers, of course. However, there's also theoretical work in machine learning, and that then, and this is why it's really not meaningful to say that statistics is different from machine learning. Same goes for artificial intelligence. That's a term that came up even more recently than machine learning. So machine learning, from my perspective, has been around definitely since the mid-90s. AI, of course, has been around even longer than machine learning, but in this kind of old style logic-based AI, which is still the prominent AI field in Germany, which is interesting, but doesn't really solve things if you're dealing with quantitative data and in an applied setting. It's more kind of a philosophy thing again, this old school artificial intelligence. What I'm meaning here is kind of this new artificial intelligence, which you hear politicians talk about since 2015 or so, and that relates on the one hand to deep learning somehow, that although this is so pure deep learning and kind of neural networks, that from my perspective that's more machine learning. AI, nevertheless, or the way that I see AI, and I will give you some topics later on, is that it relates more to decision making than statistics and machine learning. Of course, you have some form of the decisions also in statistics, if you think about hypothesis tests and or classification and decision function in machine learning. But in the end, this is fairly low level, and in AI, if you're dealing with Markov decision processes and explicit reward structures and so on, then the decision component is much more prominent. And then you also know that the AI term is fairly fuzzy. So currently you don't hear much about AI because you only hear about COVID. At one point in Germany we heard a lot about AI, but then this meant things like even just logistic regression or maybe t-tests and so on. So AI, you might also know that AI had its ups and downs over the history, and it's always it sometimes gets a hype, and there was a hype right now. I think one of the big reasons why there's a hype right now is of course that speak recognition got better, and people believe that if they say something to Alexa, Siri or whatever, that this is not just a pattern matching thing, but that there's some intelligence, whatever that means, behind it. So AI kind of a hype, but I think there are some topics in AI that, at least from my perspective as a computational cognitive neuroscientist, are also interesting, and they are also interesting for data science. Now here to comics, which kind of also give you my, or two cartoons, which give you my kind of, at least my emotional approach to this statistics, machine learning, AI kind of trials. For me, it's all the same thing. So I've taught machine learning courses. I'm working with what I call artificial intelligence models, namely things that relate to Markov decision processes and partially observable Markov decision processes. I like maybe statistics best of all of this, because somebody has their mic on. Can you please turn off your mic? But I can also try to. Hello. Can you please? Maybe I can. Alle stumm. Okay. Now everybody should be silent again. I like statistics in a way best because it's most developed, and it's kind of most theoretically grounded. So it's most satisfying to read statistical results rather than machine learning papers where we tried out 3 algorithms, we found this is best. We don't know why. That's, yeah, nice, but let's think more about it. That's where I see statistics. Here's another cartoon which also relates to maybe students' feelings regarding machine learning statistics. Machine learning, so when I was younger, so like in 2005 and so on, I also found machine learning very interesting, because if you start reading a book, it's definitely more interesting than reading your typical statistics book. But then the question is, what kind of typical statistics books are there? So for example, in cognitive neuroscience, of course, there are a lot of psychology statistics books, and you can throw all of them away because there are too many words, and so there's too much talk and too little action. So every statistics for behavioral sciences or for psychology or something, that's all horrible. There are good statistics books, but they are a little bit harder to find. I hope I included some of them in the course, or I think I included some of them in the course, and then they are also a good read, like modern machine learning books. Yeah. Good. So that were some general remarks about data science, so that you know a little bit my personal feelings about data science and where I see this whole thing situated. And the next thing I then want to talk about is statistics, so that you also get a feeling about where I then see statistics situated. You might already get the idea that I think that everything is statistics after all. So of course, teaching this course, I think it's the most important course in your program, but I guess that's what everybody tells you. So let's go from data science to statistics. So if data science is the art of creating meaning from data, then I see specifically statistics in data science as the art of creating meaning from data and quantifying its associated uncertainty. So this aspect of quantifying uncertainty, I think that's the crucial thing that statistics and probability theory add to the table. It's not that it resolves uncertainty, it just quantifies it. Of course, sometimes you will have less uncertainty if you build a model and observe data, for example, in Bayesian inference. Then you can you have maybe less uncertainty, less variance in your posterior distribution than in your prior distribution. But what you are doing there is not that you kind of reduce the uncertainty. You just quantify how much you reduce or how much observing data reduces your uncertainty. So it's about quantifying uncertainty, and what then also sometimes is hard for people is that then statistics is over and you ish over, like one of our EU commissars said famously. Nee, ish over, that's from there, said Schäuble. I think Schäuble said at one point, ish over. In any case, quantifying uncertainty is where statistics stops, and then you have to deal with it. So this is a big problem, for example, in terms of this p-value discussion and finding statistically significant results. They are a quantification of uncertainty, and then you may, after some study, you may have more or less uncertainty. You always have some remaining uncertainty. It has been quantified. And then you need to go on and do something. So, and this is why sometimes people also don't like statistics or expect more from statistics than it can give to them. There is uncertainty. There always remains uncertainty about things after statistical calculations or data analytical calculations have been done. It only gives you a quantification of that. And then you have to deal with the fact that there is uncertainty in life, and if you have two options and one is associated with high uncertainty and the other one is associated with less uncertainty, it may be a good idea to go with the one that is associated with less uncertainty. If there are other good reasons to go with the one that has high uncertainty, because maybe there's more gain to get and so on, you can quantify these things. But in the end, uncertainty remains. Yeah. So. But it's better, from my perspective, to quantify the uncertainty rather than not talking about the remaining uncertainty, because it always remains. You always have finite data. You never have all observations. So let's make it explicit. Let's say after having learned this and that and having observed these data, there's still uncertainty, and that's the degree of what we have uncertainty, rather than to say, okay, now this problem is solved, let's do a new problem. Of course, you can say at a certain point, okay, there's very little uncertainty now, so maybe we can focus on something else and view this established. So that's all fine, but there's always uncertainty. And that's, and of course, uncertainty here is described in terms of probabilities, and this is what, yeah, my basic idea about statistics is about. There are, of course, many, or yeah, many, I don't know, but there are typical topics that are dealt with specifically in statistics university courses, and I listed some of them here. Of course, there are these two big camps on frequentist statistics or Bayesian statistics, although I don't want to say camps in terms of that there's really some fight between these camps at this point. I think by now most people agree that probabilistic modeling and statistical analysis are interesting, and there's a big bunch of frequentist approaches that then also look at certain forms of optimality. That's all interesting. And then there's a big bunch of Bayesian approaches that are also interesting, and that can also be studied from an optimality perspective, and then maybe even in a frequentist setting. And this is, I think, where things get really nice. So one of the topics that sorry, I'm mainly dealing with in my own work is variational inference, and by now people have taken up studying the frequency frequentist estimator properties in variational inference. And I think that's where things then are interesting, and then you don't have two camps, but you have still kind of a little bit of different philosophies, or at least you have to think about what these probabilities that you write down in math actually supposed to mean. So that's frequentist versus Bayesian. I'll say a little bit more about that in a second. Of course, probability theory is kind of the basis for statistical inference, so it needs to be dealt with. And then there are things like hypothesis testing, confidence intervals, which most kind of people in the behavioral sciences and maybe also the biosciences always think of when they think of statistics, because it relates to p-values and confidence intervals. Maybe they also think about descriptive statistics, which I find, okay, you can compute a mean. We don't have to spend many hours on computing a mean. The question is, why do we compute a mean? When is computing a mean sensible? And Bayesian filtering, I think, from my perspective, is kind of where the whole probabilistic modeling framework makes most of the sense and has most of its power. And decision theory then kind of goes a little bit beyond what I think of classical frequentist or Bayesian statistics into more kind of the AI world. So these are topics that you find in statistics, and of course we will cover some of them, or most of them actually. In terms of the historical development, this is from a very nice book by Bertley Efron and Trevor Hasty. If you want to learn more, I think it's mainly about the history and development of statistical inference, machine learning, and AI, rather than the topics per se, although they discuss the topics from kind of, I don't know, a historical perspective. And so it's a very nice read, but it's not really, from my perspective, sufficient to really get deep into the methods. So historically, they make this triangle between application questions, and they see statistics originating from applications questions. For example, if you think of early 20th century statistics, Fisher and Pearson and Gossett and so on, of course they had really concrete problems in mind, and you might know that a lot of these early 20th frequentist statistics was developed at Rotterdam, at this agricultural center. So the question was how to test whether a certain crop is better. So that was a very applied problem. And then, of course, people start to think, and more people start to think, and everybody starts, and more people start to think, and people also try to teach this. And if you teach this, you want to make sure you understand it, so you try to put more meaning and understanding in there, and then you try to be more formal and more precise and so on. So this kind of statistics approach went from this applied setting into a fairly mathematical framework, which was then really well established by the mid 1950s. And then, of course, there are it goes on, so you can bring from 1950 on, you can bring computers in, for example, for doing Bayesian inference using random number generator methods like in MCMC, and then again at one point things become more interesting from an applied perspective, and it goes back and forth. So my prediction would be, for example, with neural networks and the current deep learning hype, it currently there's kind of some, okay, it went into computation, and then we can apply it here and there, and it's happening, for example, in medicine, where now neural networks, which could have been applied often many years ago already in these circumstances, are now being applied to certain medical questions. At one point, people will ask again, after certain things work and others don't work, why, and it will go a little bit more, the development of the field will go a little bit more into the development of mathematics, and so on. So it's playing back and forth. So here are some key dates for the last 120 years of statistics. So you might know that all of this frequentist statistics early on was developed between 1900 and 1940. Maybe if you want, accumulating involved statistical decision theory and sequential likelihood ratio tests. Then there was so the Bayesian school argued a lot against frequentist statistics and tried to build or rebuild, let's say, the Bayesian probability inference framework and point out inconsistencies in the frequentist setting, maybe exemplified by Lindley, sorry. And then more and more computer aspects played a role. Then up to the 90s and the work by Vapnik already on the 80s, so in Russia, that from my perspective then led to, because Vapnik, what he had in mind, that was a little bit different from classical statistics, so he kind of associated more with computer scientists, and this then led to the development of support vector machines and this kind of not hardcore but core machine learning aspects. And then the rest of the story, I guess you know that at one point neural networks which have been around also in parallel. So this is focusing is more the statistical work. Of course, there was AI work and psychological cognitive science work already at this time in terms of the perceptron. Then you know that there was the AI winter, and then there was a new interest in connectionists in the 80s. This is not listed here because we're looking more at statistics rather than machine learning. But then you know that at one point, neural networks performed a little bit better on recognizing MNIST than support vector machines, which then meant that the neural networks people were there again and called this thing then deep learning. Good. 3 slides on core content on statistics. So of course statistics builds on probability theory, and the basic idea of probability theory is of course that chance processes can be described mathematically. You might know that probability theory originated from trying to describe games of chance, so how to win in a casino essentially. Of course, so randomness in the world, or perceived randomness, kind of exists irrespective of whether you have a mathematical model of that or not. But the idea is that you can use it, that you can use mathematics to describe them, and you can use mathematics to make predictions about random events, which then also have proven to work essentially. And then of course if you go deeper into probability theory, and of course the mathematicians in the audience will know that reasoning about uncertain events is naturally related to measuring volumes. So if you really go into probability theory, you encounter of course measure theory, and then you have this central postulate that somehow and also that's where Kolmogorov of course developed his fundamental idea about probability spaces from, that you relate measure theory and reasoning about uncertain events. Frequentist inference is mainly the idea that you can interpret probabilities as limiting relative frequencies, which actually exists in the sense that there is really a probability for dice to come up 3, and this probability you can determine by throwing the dice many times and recording how often you get 3. It's always a little bit hard for me to really buy into this because if it's a limiting relative frequency, of course it means that you have infinite observations, and nobody will have ever infinite observations because I mean not any human will have that, because we all die, and whether humanity makes it into infinity, I'm also not quite sure. It's also an idealistic viewpoint. So in this sense, it's also not completely not objective. Um, what is central to frequentist inference is that you assume that there are certain parameters as fixed unknown constants in the world, which we will often call true but unknown values. If you deal with these parameters and you try to estimate the true but unknown values, you estimate them usually in a pointwise manner, for which you might give some frequentists, so data-related probability boundaries, but you don't make a probabilistic statement about a parameter value per se. So you don't say the probability that a parameter is larger than, I don't know, 0.5 is 0.7 or something like that, because that's what you do in Bayesian inference. You don't do that in frequentist inference. You have different criteria for these kind of interval estimates, which we will of course come to under the label of confidence intervals. And then of course you try to design methods to have good long-run frequency properties, and by looking at the sampling distributions. So that is what we will see in terms of asymptotic statistics. Bayesian statistics interprets probabilities as degrees of beliefs, not limiting frequencies. That means that you can have kind of statements like the probability that it will rain this afternoon is 0.5, or the probability that Biden will still win Georgia is, I don't know what you think it is. I would say 0.5 because I don't know. But of course that's not a relative frequency, because Biden will only win Georgia, I guess, once this year or not this year. Maybe he will run for president again if he's still alive in 4 years, if he makes it to president, but it's definitely not a limiting frequency in terms of many observations of this event. But nevertheless, you can talk about the probability of that happening. Again, parameters that you're trying to estimate are fixed unknown constants, and you make probabilistic statements about your uncertainty about their value, and you make these statements in terms of probability distributions, and from these distributions, so posterior distributions, you can make further inferences like point or interval estimates. So you don't look at primarily, and as a first textbook approach, you don't look at the frequencies properties of Bayesian estimators as a criterion, but you look at them whether they are coherent with your probabilistic model. However, at the very end, in the last lecture, we will actually look at frequentist properties of Bayesian estimators in terms of the Bernstein-von Mises theorem. But that's in the end of February. So that was a little bit on kind of very basic content relating to statistics. Before I then go to the course and discuss formalities and things, let me briefly point out some topics that I hope you will do in the machine learning course, and I hope there's a machine learning course happening. So from my perspective, typical topics in machine learning are principal independent component analysis, things like logistic regression, linear discriminant, support vector machines, kernel methods, and then graphical models, latent variable models, although they are also fairly strong in statistics. If you think of factor analysis, for example, generalized linear models, neural networks, deep learning, and things like Gaussian process regression. These are things that run under the label machine learning. If you want a course on machine learning by myself, as I already pointed out, I taught one in the summer term. There you can see me talking about things like neural network, support vector machines, and Gaussian models and so on, if you're interested in that. And then topics in AI, I mainly see Markov decision processes, partially observable Markov decision process, and reinforcement learning. And this is actually stuff that I've taught occasionally, not very much, but my actually real work that I'm doing is actually happening in this kind of area, relating mainly to partially observable Markov decision processes, because human cognition, I think, can be best discussed from a scientific perspective in the context of partially observable Markov decision processes, where, because humans as cognitive agents don't have access to the state of the world directly, but have their perceptual apparatus to make sense of the world and try to survive and procreate, so they have some target functions that they try to optimize, and so this is, I think, where cognitive neuroscience and cognitive science is really situated. So these are the methods that I'm mainly using in my own research. Relating again to this idea that there are statistics, machine learning, and maybe artificial intelligence, there are often the same things that just have different names. So in statistics, you of course have data. In machine learning, you might often call this training data. Of course, that's just data. In statistics, you often want to estimate things, whereas in machine learning, you learn things or you train an algorithm, but this is the same thing. You estimate parameters. Frequentist inference doesn't really exist in machine learning, is never really caught up in machine learning, or at least as far as I know by now. Bayesian inference, of course, is also prominent in machine learning, as I already mentioned. And yeah, this is an example for some terms. So in statistics, you might call them covariates, whereas in machine learning, you call them features, which are just aspects of data predictors. So don't get confused. Often things mean the same thing, and in a way, it's also your task in your courses as data scientists to figure out where all the things are similar. And if you ask someone, is this the same as that, then yeah, it's usually actually the case. Good. So that was my kind of content-related introduction to data science and statistics today. The next thing that I want to do is introduce the course on statistics for data science. Maybe before we go into the course for statistics for data science, which is then really talking about the formalities of the course, what you have to do and so on, where you will definitely have many questions, let's take a brief break. But before we take the break, are there questions regarding the stuff that I told you so far, or comments that you want to add to what I said about the big kind of topic data science, and then the more or the partial topic there, statistics? Are there any comments or questions on these two sections that I talked so far about? If there are questions, actually, and also to establish this at this point, just turn your mic on. Actually, I saw that that was maybe that has been around for a long time, but you don't even have to use your mouse. You can also hit your bar and then you can speak. Okay, there seems to be a question because I hear something. And what I wanted to say is just ask the question. So does somebody have a question? That doesn't seem to be the case, so then I suggest we take a break. So let's continue at 8:40, and then I will tell you all about the course and what you have to do.
Could I ask one question again?
Yeah, if it's regarding data science and statistics and not regarding the formalities.
Okay, then not.
Good. Okay, then let's continue at 8:45. Let's continue at 8:45, 8:45. We start talking about the course. Okay, so then let's continue. Just need to check my mic, sorry for that. And now enter what you might, at least today, or maybe for the whole course, maybe more interested in than the content, namely how you or what we are doing and how you pass this course. Oops. So that's the outline of the course. So we have 15 weeks this term. As you will know by now, normally it's 16, but that's the COVID bonus that you get, so there are only 15 units. Today we are doing the introduction, and then we're going to do 6 sections on probability theory. Basically a refresher in probability theory, covering things from probability spaces, random variables, joint distributions, random variable transformations, and then expectation, covariance, inequalities, and limits. And this will, oops, there's a typo, that's the 12th, that's December, so we're not going to travel back in time. And that will basically be it until Christmas then. Then there will be the Christmas break, and we will start again on the 8th of January with sections or sessions on frequentist inference, essentially leading or essentially dealing with estimator properties and optimality theory of properties, and then the important notions of confidence intervals and hypothesis testing. And then we will do 3 sessions in the end in Bayesian inference. I sent around a link to last year's course. You will notice that things were a little bit different there. We had one session on non-parametric inference. I took that out. There is a whole course on non-parametric inference by Frank Konitschke, which I aware that data science students can choose. And so if you are interested in non-parametric inference, I really recommend to choose this course. And this one session on parametric inference then wasn't not really meat or fish or whatever you want to call it, because it was quite short on non-parametrics. We just did histograms and kernel density estimators. But you can of course still watch it. We had a little bit more on Bayesian inference last year, but I think some of the things were not that Bayesian after all. So numerical methods, that was not too Bayesian. Bayesian filtering is kind of the most important thing in the whole world. But then it's also a little bit beyond the standard framework. So I focus on kind of more Bayesian core topics in a way here, but also talking about variation inference, where I'm kind of working with, and then in the end to kind of make this parallel, that you can talk about the properties of estimators both in the Bayesian and the frequentist setting. I included a new section on Bayesian estimator properties. And so that's the outline. You will have seen, let's have a look what's here. Let's stay at this for a second. You will have seen that there's last year's course, and the things that are labeled here will be, under things like finite sample estimator properties and so on, will be fairly similar to last year's course. But I try, of course, to make the course better. So here and there, take out something or put something new in. I highly recommend that you look at last year's course if you want to prepare for sessions. Like I said, the lectures will happen on Fridays, and of course I will finalize the slides for Friday's lecture only on the Thursday before, because I need to get into the settings. So have a look at, if you want to be ahead a little bit more on the schedule, have a look at last year's course. It will be really similar. I just hope to remove typos and certain kinks and so on, but it will be fairly similar. So you have, what I'm telling you is essentially you have all the material for everything that's on the slide except for Bayesian estimator properties, which would be a new section already on the web. You have videos for that, you have the slides, and you have of course also exercises for that. The principal reading material or the key references are these books, and mainly I think most of the stuff in the beginning is based on this De Groot and Shervish book, which is a really nice book. The overall outline is maybe mainly inspired by this Wassermann book, which is also very nice. Certain things in when it comes to Bayesian statistics, but also when it comes to estimated properties and things like Fisher information and so on. This is from this also a very nice book by Held and Bove. And yeah, a really good Bayesian book is this. I don't think we delve too much into this book. I will on each session slides there will be a beginning, some bibliographic remarks that will specify a little bit more on which chapters and which sections of which book the specific session or the specific lecture is based, so that you have background reading. And I highly recommend also to do that background reading. Because there's only so much you can get from a lecture. It's a different perspective that you get from the textbook. Of course, the content will largely be the same. I, of course, condense things. There's much more in the books. You will find much more material in the books than you find in the lecture. But that then, gives you a lot to read and a lot to study. And these are really, really good books. So I highly recommend if things are really new to you in terms of probability and statistics, this is your method of choice. If you feel like, because you're coming from a mathematics or statistics course, you know all of statistics already, I think this is a really nice refresher. So that you again think, okay, I remember that was Markov inequality, Chebyshev inequality, yes, I remember, and so on. This is Fisher scoring and so on. If you have heard all these terms, this is a nice refresher on that. This is a nice book if you have mainly dealt with frequentist statistics in the past and are now trying to incorporate Bayes in there. And if you're really interested in Bayes and the theoretical foundations, then I recommend this. To make it clear what these different aspects of the course are about. So there is the Vorlesung, which is happening right now. This is where we cover the core course content. It's about knowledge acquisition and breadth. So we try to cover a lot of ground, and it's for me it's really important that you learn something. I know that a lot of courses are mainly focusing on you that you do something. You're also supposed to do something here, but I think there's a lot to learn, and it's before you start doing things without knowing what you're doing. I think it's good to know a lot. So I emphasize knowledge acquisition definitely. And that's the Vorlesung. In the Übung, you will need to do something and actively participate. So that's where I will test your active participation in the course, whether you are actually following along. It's of course, reviewing things that we did in the Vorlesung. So it's about knowledge consolidation, and here and there we go a little bit more into depth than in the Vorlesung. There are things that will come with the course, which are the study questions, the theoretical exercises, and the programming exercises. So the study questions try to focus on certain aspects of the lecture, emphasize what is important, and will be the basis for your exam. There will be an exam, as I will tell you in a second about. There are theoretical exercises and programming exercises which we will deal with in the Übung. The theoretical exercises are mainly to go more into theoretical depth and also to help you with your self-study to assess whether you really understood what's going on. The programming exercises help to get an intuition about all these probabilistic concepts, which I think are easiest to deal with if you look at them from a sampling perspective. Of course, they also allow you to go a little bit into low-level Python programming, dealing with NumPy arrays and so on, and visualization. So that's what they also help with, and then of course also with to a certain degree with application of the concept that we discussed. And then there will be exam, and in the exam you are required to reproduce knowledge, so it will not be kind of a transfer exam where you will have a problem and then the question will, which kind of statistical methods do you best apply and why? But I want to make sure that you know statistical methods and that you can reproduce things, and so that you then, after you know a lot, later in your life are able to apply things based on what you know, and not trying to have you apply things without you knowing what's going on. That's a lot of people try that in courses, and I don't like that. It doesn't work. So course requirements, and we have two types of students here, and now you all know who you are. So if you are either a data science student, so you are registered in the Master Data Science, or you are not. This is now for those people who are data science students. There are these two main components, the Vorlesung and the Übung. For the Vorlesung, there is a written exam. This written exam is pass or fail, because that's according to the study regulation of the Master for Data Science. The reason that it's pass or fail is that there have to be courses or modules that are pass or fail, and no lecturer wanted to have their course to be the pass and fail course, and because I'm a nice person, I said, well, I don't mind, and then I have the pass or fail because we have to do it. So it's pass or fail. There will be 30 questions, and the exam will be 90 minutes. There will be 2 questions for each of the 15 units, including this introductory session, and you get maximally 1 point per question. You will know all the questions beforehand, because the exam question pool corresponds to the study questions. The study questions this year are shared with the lecture slides, so they will, in the end of each lecture, there will be a session, or there will be a section on exercises, and the first part of exercises will be study questions. And so you know all the study questions, and as you will see, the study questions essentially want you to reproduce definitions or core concepts from the lecture slides. So this is also with regards to the exam. Although I recommended books and so on, the content that I will test in the exam is based on what we do in the lecture. And the final study questions pool is the one that is provided with the lecture slides. Of course, here and there I will have made a mistake, and there might be typos even, or I have a question in there that somehow is not a sensible question and so on. Most of the study questions are fine, but this can always happen. So I will, if something like that comes up, I will of course update the slides on the website. And in the very end, before the exam, of course, there will be no more changes regarding the study questions. And the study questions are also very similar to the study questions from last year, so you have all the study questions already. So if you go to the exercises on last year's course, you have all the study questions, and in essence you actually have more study questions there than you will have this year, because certain sections don't come up anymore. With regard to the pass or fail, you need more equal to or more than 15 points out of the 13, and you need to have at least 1 point out of the 2 questions of each unit to pass. This is of course to make sure that you study all sections and not only the first 7, and study them. So this 1 point of the 2 question doesn't mean that you have to have at least one completely correct. You can also have 0.5 points in one of the 2 questions and 0.5 in the other of the 2 questions. So the sum matters. But for the 2 questions of each unit, you need at least 1 point. It's not hard, it's just memorization and studying, and people did very well. Last year, specifically those students who needed a mark, which were not the data science students, but a lot of other students, and there were a lot of people who needed a mark and who actually got a good grade. So it's doable, there's no magic about it, but it requires work. So you have to do the work, and you have to study, and you have to memorize. But you know exactly what you have to memorize, and if you memorize all of it, you will be rewarded. There are no tricks or anything. So, and there are no kind of transfer exercises that depend on how well I formulate the question and so on. You have all the questions beforehand, but you need to work. That's the main thing, and memorize and understand. There are 2 exam dates. The first is on the 5th of March 2021. That's a Friday. And this is the actual exam date. If you fail that exam date, if you fail there, you can retake the exam in this academic year 4 weeks or 3 weeks later, namely on the 26th of March. And yeah, that's essentially it. You can also choose not to take the exam on 5th of March and just be confident that you will pass on the 26th of March. You can do that. It's a gamble because there no other dates will be offered for that in this academic year. So I really recommend to take it on the 5th. If you are sick and you have a doctor's notice that you are sick either for the real exam date or for the exam reset date, of course we will find another date to do the exam, but only you really need a doctor's notice. It's not that you decide not to come because you're not prepared enough or something. That's not enough. So you need to, it's a proper exam date. You need to show up, write it, and if you fail, you can retake it once. If you fail both exams, you can retake the course and you can retake statistics for data science. There are, in principle, I think there's a limit of 3 attempts of trying a course, but then because of Corona, that is not happening anyway. So if you fail statistics for data science this academic year, you can do it again next academic year. If you fail next academic year, you can do it again and again and again. So it's not that anyone will throw you out of data science because you failed the exam, but you will have to retake the course, including the Übung and the active participation. So in the Übung, everybody who is in data science will have to present one theoretical or a programming exercise. That's for those people who are here, who were there last year. That's also different because I think you had to present one theoretical and one programming. This year, all the data science students only have to present one exercise at all, and they can choose whether it's a theoretical or a programming exercise. And to get the active participation, you need to submit a Python script with honest solution attempts of all programming exercises. Your colleagues from last year can tell you what counts as honest solution attempt, because I mainly check whether you tried and whether there's something going on. If there's nothing, then that's not an honest attempt, but it also is, you don't need to be for most of the programming exercises, there isn't one correct solution or something like that. So you need to try to do something. And the main thing that I'm emphasizing to do the programming exercise is because they help you with the understanding of what you need to learn. And if you ask people from last year who really did the programming exercises, and most of them did them actually quite late, they did them really after they maybe even took the exam, they say, and I agree with them, and that's how they are designed, that they learned something by doing the programming exercises. So Do them, and what I really recommend is that you do the programming exercises together with your studying, because that's what they are designed for. Yeah, whether you study all along or you say, okay, I want to study only in February, that's all up to you. But do them together with your studying, and to encourage that, the deadline is the 26th of March. So that's well, it doesn't really encourage that. That's the last, that's the second exam date. So you can choose to first take the exam and then do the programming exercises. If that's how you think things should be, I don't recommend that. We will talk more about the exercise in the Übung, and we will actually have that today. So I want to stop at 9:15, so we will be able to address many more questions today in the Übung, because that we won't have any presentations and so on. So bear with me a little bit. For those people who are not data science students and who take part in this course, you're very welcome to take part in the course. Most of you will need a grade, so you will have a graded exam. So it's not pass or fail, but of course you can also fail if you have less than 15 points. It's the same exam as the data students will get. Of course, then the same constraints apply. So you have the exam question pool and so on. The dates are the same. The only thing is that you will get a grade, you will get a mark, because you will get a mark, you will not, and it's not only pass or fail. So you basically, if you want to perform well in this course, you need to study everything, or the other people can maybe try to study half of it and be lucky that that gives them 1 point out of each unit. You need to, for active participation, submit all programming exercises as well as the data science students, also by 26th of March, but you will not present something in class. The reason I'm doing that is because the master, because this course was of course designed for the data science students, and of course this one-to-one tutoring that I will offer in the Übung when people present something and I will ask them questions about this. This I can only offer for the data science students, otherwise there are too many, and also it wouldn't really benefit if we have too many presentations. We had really many presentations last year and most of them were quite bad, so it was a huge waste of time. So I'm trying to optimize things there. So for those people again who are not data science students but who are joining us from other programs, feel welcome. There will be an exam, you will have to do programming exercises, and you will get a mark. Good. Behind this there's exercises. Okay, we keep that for later, so we can do a round of questions now. We can do 10 minutes of questions, and then I have to stop this because I have to go to the next course. We then meet again at 1 p.m. and continue our question round. Okay, so hit me with questions. Good, so this is then the start of the Übung part of statistics for data science, exercises, and let's go. So the first thing, as I said already this morning in the lecture, at each end, so at the end of the lecture slides, there will be the exercises, and that's different maybe to what people were used to last year, but this is how it's happening this year. And the first thing will be the study questions, and these are now the study questions for today's lecture. And as I said, the study questions are for you to revise, rehearse, and memorize the content of the lecture, and maybe to focus it, and they will be the pool for the question pool for the exam. So with the study questions, I think in the exercise sessions we will hardly deal. They really relate to the lecture content. Of course, the theoretical and programming exercises also relate to the lecture content, but yeah, I mean, if we would go over the study questions and the exercises, we could just have the lecture again. So that's not
what the aim is, but you should look at them, study them, find answers to them, and get ready to perform well on the exam. Now, the core thing about the exercises is that you obtain your active participation of this module. And what I already outlined this morning is that it differs slightly between a Master of Data Science and non-Master Data Science students. Both groups of students who want to complete the course need to submit honest solution attempts for all programming exercises. And the data science students, in addition, need to present one theoretical or one programming exercise in class, meaning in this exercise session. And the presentation should be maximally 15 minutes, not longer. And it depends a little bit on what you choose to present. So it can be a theoretical exercise. Then I asked you to prepare a Beamer presentation. Yeah, I think there's no point in using PowerPoint, so you should prepare a Beamer presentation where you then discuss the content of your exercise. If you're doing a programming exercise, you should use a Jupyter notebook for the reason that I also expect, if you are doing a programming exercise, that you first kind of lay out the theoretical background. Most of the programming exercises will be to simulate one of the probabilistic statements that we see in the course. So then I expect that you first review what you're actually doing, and that's where Jupyter notebooks come in handy, because they allow you to also write some math there. These presentations or active participation criteria can be failed. So this is what I also wrote here. Think of the presentation and a subsequent discussion. So I will also ask you questions regarding your understanding of what you're presenting. You should think of it as a mini oral exam. So you can fail the active participation, except for those who present next Friday. That's the little benefit of deciding to present next Friday, which of course is not that much time to prepare, but it's a week, so it's definitely enough. And for people who are from mathematics and have done some probability theory, the exercises are really simple. So the active participation can be failed. Next week it can't be failed, but what you can get, of course, from next week is, if you have a look at what your colleagues present and how the interaction goes and so on, you can get a good feeling of how to fail or not, or how to pass the active participation. But so the original idea I had for the Übung this year was to have little tests every week. But this, of course, would only really work in the presence mode, that it can. So because I want everyone to work on the stuff, which was a little bit, which didn't really happen last year because I didn't enforce it. So unfortunately, are under a more tight regime. You will have this one mini oral exam regarding one of the one exercise. There's only one. To help you with the preparation for that, I can give you feedback on what you have prepared so far, so meaning your Beamer presentation or your Jupyter notebook, by Tuesday before the presentation. Only on Tuesday, so not earlier, but also definitely not later. And then by looking at your presentation and assuming that you know what's in the presentation and that you understand what you're presenting, I can tell you whether you will likely pass or fail the presentation based. So please wait with questions until we enter the question thing, because there will be many questions, I guess, regarding to this. And so I give you this feedback, and the question is, of course, what are the exercises and how do you sign up for that? And this I will send you by mail. Maybe I actually already sent it to you, but I can show you where this is located. Too late. So it is really good in Python programming, except myself. Turned out that wasn't really the case. You are doing a programming course with Python, I think, as we speak. So you should, so in the data science cohort, you should know what's going on with Python. Nevertheless, there are certain things that you will particularly need to work with the programming exercises. As I said, most of the programming exercises are simulations, random sample simulations of results that we discuss in the lecture. So it's not programming to analyze some data and find which disease somebody might have, but it's programming low-level methods programming, if you want, and methods validation for statistical inference. And for that, what you should be familiar with are NumPy arrays. So you can work with pandas, but it's just annoying and way too much overhead. So try to program a little bit more level C++, or let's say MATLAB style. So use NumPy arrays for everything. For all the random aspects, so like sampling random variables, plotting probability density functions, probability mass functions, and so on, use SciPy_Stats. It has a lot of things. So let's see whether we get there. And nothing breaks. Yeah. So SciPy_Stats is a module in the SciPy package, and it has extensive functionality for if you want probabilistic programming. So you have all the continuous distribution, multivariate and discrete distributions that you may want to imagine and that you need for your exercises. So that's very good. So use this for sampling. It makes the code nice and clean. And then let's go back here. For plotting, use low-key things. Use matplotlib. Don't use Seaborn, which does fancy plots without you knowing what's going on. Go to the basics and make basic plots. So that's kind of the approach that I'm encouraging here. That said, like I said, I want honest solution attempts, and in the presentation, again, honest solution attempts, but it's not that there is only one correct way how to do things. So these are just my recommendation. Use NumPy arrays, use SciPy_Stats, use Matplotlib for your visualizations, and that's essentially all you need for all of this programming here. And to exemplify what I mean there, and what also happens in a lot of these exercises is that you sample some random variable, then you might apply some transformation to it, and then you look at what the result of this transformation is and compare it to a theoretical result that we discussed in the lecture. So that's the basic structure of essentially the exercises. And to exemplify that, I want to briefly show you how this is done for the basic case of sampling a univariate Gaussian and then plotting the PDF of a univariate Gaussian on top of it to compare the histogram of your samples with the PDF. What a PDF is, we will discuss, of course, from a mathematical perspective in the course, but I assume that all of you have seen Gaussians before and all of you have at least some understanding of what PDFs are. So yeah, to get started, I assume that you roughly know what I mean by this. So let me show you how I envision your simulations and so on to work. So this is now oops. Okay, thought my keyboard wasn't working. There we go. This script demonstrates sampling and visualizing a Gaussian random variable. What I particularly is important when you write code that you include a lot of documentation. Please write clean code, comment and structure your code. Don't make a mess, because a mess doesn't help anyone. So what I usually do is that I import some general utilities to save stuff and have nice path properties. I import this OS, operating system functionality. This is not that crucial. Actually, I only use it at certain points to save figures, essentially. Same goes for this sys module. That's for system utilities. You will see how I use them in a second. They don't really relate to what we have in mind. But then, of course, NumPy has to do. So you can work with NumPy to get a lot of numerical programming done. That's NumPy. And I assume Sandro, if you haven't heard about NumPy, Sandro will tell you about it. And then, and this is now specific to what we are doing, and that can as well be that Sandro is not telling about it. We are using this SciPy stats module for, or it's a good idea to use this SciPy stats module to deal with random variables. And then, yeah, I'm using some basic matplotlib functionality for plotting, visualization module maybe, and color map. Sometimes import color map, don't need this now. And what I like to do is first is to close all figures. So a lot of these simulations are of course there to simulate simulate and visualize things. So to don't get too many open figure windows, I close all figures. So let's save this. No, it's 1. See whether we have a bug already. No, that looks fine. Yeah, and then what's a good idea is if you annotate your graphs to use tech for that. That's a parameter that you can set so that you activate tech. It's not awesome, so for certain things from AMPSimp and I think even AMPSmath, I haven't really figured out how to get this into Python, so there I actually have to, hopefully will figure out certain things more, but to have some basic LaTeX stuff there definitely already makes sense. And then often you will have subplots, not for what I'm doing right now, but I have a kind of a structure that I'm always using. I use GridSpec for subplots. In a way, what I'm trying to do here is recreate everything that I'm familiar with in MATLAB in Python, because MATLAB is a good thing, but we are, of course, in data science here, and we and Python is also a good thing. So then it's always good to do some directory management. So if you want to save your figures, that you know where you save them. So we get the working directory here using this OS functionality, and that's a good thing. That's the working directory. So the way I'm writing and debugging stuff is that I always put an arrow in there to then investigate. So that's my working directory right now, and then I decide on a figure directory for which I join the absolute path, and then this is long, sorry, zep join working directory to split this, and use this and go up to one level above it, and then use my figures folder which I've previously created. So that's my figure directory. Let's see whether that is doing what it's supposed to do. Oops, that's a typo. Good, that looks good so far. So this is all just overhead, initialization overhead, but gets me into a working position. Now I want to start with this thing of sampling and visualizing a univariate Gaussian, whatever that is supposed to mean. So what I want to do is sample a Gaussian and plot its histogram, and on top put its PDF. So would have been good if I had actually the code to do that here, and now I realize that I don't. Let's see how far I get. First thing is to sample some Gaussian, so we need to decide on a sample size. So let's go for 200 for the moment. And let me briefly go somewhere else so that we don't run into big problems here. So just as a backup. So we now have specified the sample size, and if we now want to sample it, we can use the SciPy stats module. If we go back to SciPy stats without crashing my machine, hopefully. Doesn't want to do it. We can use the RVS property. So the way that SciPy stats works, I have it now I've imported it, and then you specify the distribution that you are interested in usually. So for example, a normal distribution or a chi-square distribution, and then you have three three types of functionality always. One is to sample the random variable. That's then always, so let's do it like this for the moment. This is where your distribution of interest is. And then you can sample that using RVS and then some parameters usually. So parameter 1, parameter 2, and then how many samples you want. For the same distribution, you have the option to get the PDF or the PMF. Again, depending on whether it's a continuous or discrete distribution, and you also get the CDF, so the cumulative density or distribution function, and you also have the inverse CDF, which is not called ICDF, which would be sensible, but which is called PPF. You have for each distribution that you're interested in, you have the basic things that you need, so a random number generator, a way to evaluate its probability or probability mass function, a way to evaluate its CDF, and a way to evaluate its inverse CDF. If you're not familiar with these terms, you will after we discuss them, but you have everything that you need, and that's good. So let's now try to sample first our normal distribution. So if you know what a normal distribution is, or univariate Gaussian, you know that it has an expectation parameter, so let's use this, and it has a variance parameter, let's use this. So that's our expectation parameter, and that's our variance parameter. And well, maybe let's first visualize its PDF, so for which we also use RVF norm now. So if we want to visualize the PDF is of course a function of the outcome space of the random variable. So let's set up the outcome space. So we set up a minimum x value that we're interested in. So for example, -3. Minimum x value, x maximum x value, let's say 4. And a resolution of our space, let's call this, or let's use 200 at this point, 100, sorry. And then let's create our space here. That's our random variable outcome space. So now not much has happened. We've just created a vector of numbers between -3 and 4 linearly spaced. So let's see that this is all fine. So oops. Here we now have our numbers for which we can evaluate our PDF of interest, which here is of course the Gaussian. So before we now sample that, let's visualize the PDF to already know what kind of samples we expect. So the way I'm doing it then here is always to initialize for visualization purposes an axis set. Of course you can do that differently, but I find this quite helpful. Then choose some sorry, I forgot something. Sorry. First, of course, need to initialize a figure. I'm using pyplot to initialize a figure, and yeah, you can decide on your figure size so that it looks nice. So let's use what I have here. So this just creates a figure window. Oops. Let's see that this is all working fine. So
So that's there, that's good. And then usually I specify my subplot structure at this. For this, actually, I only want one subplot, so that's not too interesting. So I just do this. And then usually in my access set I have multiple subplots, but here I'm just having one, and I'm taking this one subplot in there, and this then initializes my, or creates subplot of interest. So again, this is all just essentially overhead to, no, it takes a little bit to create something that I can plot on. And now we actually want to plot something, and what we want to plot is the PDF. So we want to plot the PDF of the univariate Gaussian with the parameters that are specified here, so mu and sigma square here, and that of course can be done using the plot function. And there, of course, we need an x and a y argument. So our x we created up here, and now our y is the PDF. So we use the CypherStats module to plot the PDF. So again, for any distribution, you put the distribution name in here. Of course, you need to look up at the CypherStats website what's the name of for your distribution of interest, and then again you have the PDF or PMF, CDF, ICDF, so PPF, and the RVS for sampling for random number generator options. And this is why I also highly encourage to use CypherStats rather than the NumPy random number generators, because it's much more coherent and structured if you use CypherStats. And then, we need to specify what we want to evaluate. Of course, we want to evaluate the PDF over X, and then we need our parameters. And the strange thing that in all programming languages that I know, the univariate Gaussian takes as a parameter the standard deviation. The multivariate Gaussian takes the variance. From my perspective, it always would make more sense if it always would just take the variance, because that's how it's defined. But that's how that is. Let's give it maybe a little bit of a bigger line width and have a look. Is everything fine? I think I gotta drag it too many. So we've now successfully plotted a PDF of a Gaussian. It's of course not the most exciting exercise. Let's make this a little bit bigger. Have a look again. Good. Then let's make the plot a little bit nicer. Of course, you can also set defaults for your for all your figure properties, and I highly encourage that. And please make nice plots. And you find a lot of stuff, for example, in this Towards Data Science website, how to make plots nicer. So, for example, by removing these box things, which I'm currently doing. So this should also be gone. So that looks already a little bit nicer. And then let's make the font size better.
Okay, that looks a lot nicer. And then if you want to print this actually and save your figures, which is of course always a good idea, this tile layout functionality is quite helpful. So that's is kind of cut to plots of interest. This is here plotting the PDF, and this is remove box, or part of the box obviously, and this is font size, and then it's fairly easy to save that using Fig, save Fig, and yeah, using this path you can then nicely join your figure directory with your figure name. So let's call this STS0 Gaussian PDF hist, and save this as PDF. And you can have other parameters like how many dots per inch, like 300 for example, and as format take PDF. So that's the printing of the figure, so that it gets saved. Let's see whether something goes horribly wrong. No, it doesn't seem to be the case, so now it should also be saved. I guess here, yeah, that's where we have it now. So that's our plot that we just created. Oh, that's pretty big. Oh, because this is still open. Okay. Good. So that was basically plotting the PDF. Maybe we also label the axis a little bit. So let's do some axis labels and make that really nice before we plot the histogram on top. So x0 set x label. Actually, I like the, you will hear that from me all the time, I like the way that MATLAB does things by now a lot better, because this is still how MATLAB did things like 10 years ago, that you need to call functions instead of just setting the properties of these things. But so be it, it will be there at one point, I hope. So now we have a little bit of an X label. Let's make this a little bit bigger. And then I guess we also have to make this a little bit bigger. Is this the, no, whoops, sorry. That's the, maybe it is. So, and yeah, if you're plotting multiple things on top of each other, what's also helpful is that you put a label to your plot. So in this case, let's let that be the PDF of a normal distribution, which we will write mathematically like this, as we will learn, and then put using the format function, use the parameters that we're actually using. So that's our label. Let's see, there's something wrong. Maybe a bracket too many. Okay, that's still working. We will not see this label yet. That's also a little bit too much. Let's make this bigger here. Because you only see the label once you put in the legend. So let's put in a legend. Because if we're plotting stuff on top of each other, it helps to keep track of what that actually is. And That's our legend, or yeah, let's call it legend. That's our X label. So it didn't like that. Okay, this is because I forgot to close the LaTeX formatting. Now that worked, so we can definitely make this a little bit bigger. Let's do this and turn off the frame. Maybe a little bit too big, but so that's basically making a plot in Python using matplotlib. Of course, there's nothing fancy here, but it seemed to be a little bit of a problem for last year's students. We can also set the y limits, but that's fine. So let's now take also a random sample. So that's our sample size, and then we can use scipy_studs to create a sample. So rv norm rvs mu again np square root 6 square, and I think that size equals n. Let's check. So now we created a sample of independent univariate Gaussian random variables, and we sampled 100. So let's increase that to 1000. Oops, sorry. So now we have many more samples, and now we want to sample Gaussian using scipy_studs, and now we want to plot this histogram of the sample, or let's say we want to first plot the histogram and then plot the PDF on top of it. So for that we can use the hist function, and this here there will not be any non-parametric stuff, so you will not learn what a histogram actually is. That was also a big problem for last year's students. It's a little bit, if you really go into what a histogram is, it requires some work, because a histogram you need to normalize appropriately so that if you're dealing with a PDF it integrates to 1. So this can easily be done by using this density option here for the histogram. Then it depends a little bit on how you set the bins. So you can specify your own bins and how many bins you have. Of course, all of these things are documented. So I looked at the documentation and figured out that this is a good way to do things. If you are new to this, of course, have a look at the matplotlib documentation for a histogram. There is no magic to it, or you're not supposed to know what's going on without looking at the documentation. So have a look, and that's a PDF estimator histogram if you want. Well, then let's have a look. Yeah, doesn't look too bad if we increase the sample size a bit more. It's looking even better. So that's essentially what you will do often in these exercises. So you use a random number generator to sample a specific distribution, and then usually you will not only then visualize things, although actually I think in the random variable case that's actually all you do. but most of the time you will also apply some kind of function to that, and then look at the histogram. For example, you will do things like sample. Let's see, that should work, I guess. You will, for example, square the values of your sample, and then compare it to your PDF. Obviously, you see that if you square things from a normal distribution, the resulting values are not squared anymore. They're actually chi-squared distributed, and then it doesn't fit with the PDF. But if you don't do anything to the sample, in this case, your histogram estimate, of course, just corresponds to your PDF. So that's kind of everything in terms of the basic programming that most of these programming exercises entail. Yeah. So make sure that you understand SciPy Stats, that you are familiar with its main functions, namely RVS for random variable sampling, PDF and PMF for evaluating probability density and probability mass function. Sometimes you need the CDF, and sometimes you need the inverse CDF, which is called PPF, and you need some basic plotting. That's about it. Good. So then I'm actually done with what I wanted to do today, and I'm happy to then again answer questions that you may have, be it regarding this programming or other questions regarding the course.